All right, good afternoon. So let's see. It's like we don't have Jada. Maybe she's going to be coming in. All right, so Tobias, I know you had a busy weekend. How about you, Weston?
I didn't have a very busy weekend.
No busy weekend for you?
No.
So, do either of you have a girlfriend that you got to buy Valentine's for?
Yeah, I'm actually going today after school.
Oh, yeah, okay. All right, yeah. Don't don't think about these flowers are gonna die. She'll just get fat on the chocolate. No, you can't think about any of that. Don't be logical. Just get her what she wants. Take her to a dance, whatever. All right, let's see. Okay, so so today we're actually going to do the last section in chapter 7. Um, so that's on, let's see, relative rates of growth is where we are. So, and this is pretty much a one-day lesson. And if you notice that even the practice problems, I don't have very many practice problems, although they do have like part A, B, C, and D or something like that. It's like 1 to 9 odd or something like that. Let's see. Yeah, 1 to 9 odd. All right. Okay, so before we get started actually on this, I want to, well, I'll wait just a minute before I stand up to the board. There's some little thing I want to read to you, but let me explain what this is all about. Is let's say that you are a computer programmer and you write a piece of code that does the job of whatever it is you're trying to get it to do. Okay. And then somebody else comes along and they write a piece of code that does the same thing, only quicker. Do you think that they're going to like the new code better than yours? Yeah. Because, see, in computers, it's all about speed. And if it does the same thing, only faster, then that's what it's all about. And so, so if you can minimize the lines of code or make it operate quicker, then that's a huge thing in the world of computer programming. Okay, so with this, in this topic here, relative rates of growth, we're talking about functions that all go to infinity. It's kind of like saying they all get the job done. But what we're interested in is which one's faster, which one does the job better. Okay. So in this example here on the board, all of these functions, y equals x squared, 2 to the x, e to the x, these all go to infinity. But as you can tell, like 5 to the x shoots up quicker and steeper than, say, x squared, y equals x squared, or y equals x. Okay? And so you can kind of see that the steepness that they go is important. Okay? Now, having said that, you can't just look at a graph. And this may sound sort of counterintuitive, but you can't just look at a graph to say which function goes faster, because they might grow at the same rate. It's just one has a higher higher y-intercept than the other. But these two are a good comparison. Here's natural log of x. goes to infinity, but ever so slowly. And e to the x shoots up pretty quickly because it's exponential. Okay? So this is the part that I want to read about to you. Okay? All right. To get a feeling for how rapidly the values of y equals e to the x grow with increasing x, think of graphing the function on a large blackboard with the x-axis scaled in centimeters. All right, so what they're saying is, so imagine if you went over 1 centimeter for the x value. Then the y value would be e to the first, which would be like 2.7, so almost 3. Okay. All right, at x equals 6 centimeters, so let's say this is 6 centimeters here, then e to the 6th would be about 403 centimeters. So basically, we're already through the roof. Okay, at x equals 10, so see x is only 10 here. Well, e to the 10th is 220 meters, which is probably higher than any building in all of Navajo County. All right. At x equals 10 centimeters. So right here, let's see. Oh, I did that one. At x equals 24 centimeters. So here's the x value. How high is the y value on this yellow curve? Well, at x equals 43. No, at x equals 24, the y value is already halfway to the moon. At x equals 43, so here's the x is 43. Let's see if I can get it down there. There we go. So at x equals 43, the y value on that curve is high enough to go past the sun's closest stellar neighbor, the red dwarf star Proxima Centauri. So yes, I mean, it shoots up super fast. Okay. Now, compare it. So now with natural log, it's just the opposite. So the x values go quickly, but the y values, although they go to infinity very, very slowly. Okay. So like, for example, to figure out how when the y value is just up to here, 43 centimeters, the x value would have to be out nearly 5 light years on the x-axis. Okay, so that's just telling you that the natural log, it is growing, but so slowly, whereas the e to the x grows super quickly. Okay, so that's kind of what I wanted us to get out of that. Okay. So what we're going to do is compare rates of growth. Okay, so we'll say that f grows faster than g as x approaches infinity if, when you do the comparison, if f is on top, as you compare f of x and g of x, if you get infinity as your limit, then that means the top function wins. Okay? Or if you if you compare the two and you get 0 as your limit, then that means the bottom function wins. And so in this case, is f grows faster than g if it's on top and you go to infinity, or if it's on bottom and you go to 0. Okay? And then f and g grow at the same rate if, when you calculate that limit, if you get a number, L. And L can be any number. But if you get a number, then that means they grow at the same rate. So like 5x and x, see, you could cancel the x's, and so the limit would just be 5. So that means that 5x and x grow at the same rate. Okay. Now, 5x and x, some people, see, this is where I'm saying that you can't just use the graph to figure out which one grows faster. Because 5x is much steeper than y equals x. And so if you just look at the graph, you might say, oh, the 5x grows quicker. You can't do that. Because, see, you might say, well, when x is 1, the y is 5. When x is 2, y is 10. So it's doubling in value. Well, for y equals x is 1, y is 1, is x is 2, y is 2. It's also doubling in value. And so its rate, its growth rate is the same. Okay? Or so like an investment of $1,000 or $2,000. If you invest at the same rate, and you say, how long does it take that investment to double or to triple? Doesn't matter how much money you start with. It's the rate that matters. The growth rate then would be the same for these two. Okay? Because it doesn't matter which one you start with has more money, then it's going to double at the same rate. Okay, so this is what our problems are going to look like in this section. We'll say compare e to the x and x squared to see which one grows faster. All right, so then what you do is you just pick one to go on top, one to go on bottom. It doesn't matter. And you say, all right, well, if I plug in infinity over infinity, then that's an indeterminate form. So this is where I use L'Hopital's rule again. So if I use L'Hopital's rule, the derivative of e to the x is e to the x. The derivative of x squared is 2x. So that's going to get me infinity over infinity, so I use L'Hopital's rule again. This time, the derivative of the numerator is e to the x, but the denominator of the derivative is just 2. And so that answer is just going to be infinity. Now, if you get infinity as your answer, then that means the numerator wins. And so then we say e to the x grows faster than x squared. All right? So you guys try practice 1A, please. All right, so Tobias, what'd you get?
I got that the e to the x grows faster.
E to the x grows faster. All right, Weston, did you get that?
Yeah, I did.
Okay. Either of you have any questions on that? All right. Now, let's say if I'm comparing 3 to the x and 2 to the x. Okay. Well, then here what you actually want to do is group them together and make it 3 halves to the x. Now, if this number inside the parentheses as it goes to infinity, if this number is bigger than 1, then it will go to infinity. If this number is less than 1, then it goes to 0. So in this case, it goes to infinity. So that means the one on top wins. So these three little dots mean therefore. So therefore, 3 to the x grows faster than 2 to the x. Okay? All right, so try practice 1b. All right, so Weston, what do you think?
4 to the x grows faster.
4 to the x grows faster. Okay? So 4 to the x grows faster. All right, any questions? All right, so let's say I have x squared and ln of x. Now, let me just tell you in general, if you were to guess, then usually ln of x is going to lose. It's going to go slowest. So usually, okay? But let's just see how it works out, or the math here. So I'm going to compare x squared and natural log of x. So you try plugging in infinity, and you're going to get, and you get infinity over infinity. So you use L'Hopital's rule. So that would be 2x over, and then the derivative of natural log of x is 1 over x. So now to simplify that, dividing by 1 over x is the same as multiplying by x squared, or by x. So you get 2x times x, which gives you 2x squared. So then when you plug in infinity, you get infinity. So that means that the one on top, x squared, did win. So x squared grows faster. All right, so try practice 1c. All right, so Tobias, what do you think?
X cubed grows faster.
Yep, that's it. So once you use L'Hopital's rule, then you end up getting infinity, so the top one wins. Okay? So let's put our little 3 dots. So therefore, x cubed grows faster. All right, so let's try natural log of x and x. So you have natural log of x over x, okay? So that's going to be infinity over infinity, so L'Hopital's rule. So you have 1 over x over 1. Well, anything over 1 just becomes 1 over x, so that's 0. So that means the denominator wins, which is x. So then x grows faster. So if you get a 0, then the bottom one wins. All right, so try practice 1D. All right, Weston, what do you think?
X squared wins.
X squared is going to win. Okay, so the x squared grows faster. All right, questions? Okay, So exponential functions with different bases never grow at the same rate. And if a is greater than b is greater than 0, then a of x grows faster than b of x. So if you have exponential functions, whichever one has the biggest base is going to win. Okay? So here's the deal again. So if I had a to the x and b to the x, if I just take the limit of a to the x over b to the x, then I regroup them so that they're both raised to the x. Okay? So if a is greater than b is greater than 0, then if a is bigger, then that means this will be bigger than 1. And so anything bigger than 1 raised to the infinity would go to the infinity, and the top one would win. If b is bigger, then a fraction raised to infinity that's less than 1 goes to 0, and so that would mean the denominator would win. Okay? All right, so do practice 1E. All right, Tobias, which one's going to win?
Sorry, would it be 50x?
Yep, 50 to the x. Because when you do the limit, and you group them together, see this number, 50/30ths or 5/3 to the infinity, that's bigger than 1. So as you keep multiplying it by itself, it's going to keep getting bigger and bigger. So that means it would go to infinity, so that means the numerator wins. Okay? Okay, so logarithmic functions with different bases always grow at the same rate. Okay? So, here we have log base a of x and log base b of x. So, different bases. All right, so you put one on top and one over the other. Now, what we're going to do here to simplify this is to use the change of base formula on each of these. So log base a of x, you can write that as the natural log of x divided by the natural log of a. And log base b of x, you can write that as the natural log of x over the natural log of b. So now, on a complex fraction, if you invert and multiply, then you're going to end up with the natural log of b divided by the natural log of a. But now remember, these aren't, a and b aren't variables, they're the bases. So this is just a number. This is a constant. So if that's a number, we're going to call it L for the limit, then that means they grow at the same rate. So if we get some kind of a number there, then they grow at the same rate. We didn't get infinity or 0. We got a number. All right, so try practice 1F. Are you hot, Tobias? Is that room hot?
Yeah, it is like really toasty in here.
Really? Because I have been so cold all day, I can't even stand it. And I'm fighting off a cold. And I think I yelled too much Friday night. And mostly at the refs, not at you. Anyway, and so I think I was catching a cold, and now today I just can't get warm. So it's kind of funny to see you move that fan. And
The funny thing is it snowed this morning and it was like freezing this morning, but now I'm dying. It's so hot.
Wow. Wow. Did you guys have like a 2-hour delay or anything like that for school?
Yeah, we did.
Okay. How about in St. John's? Did you guys have any kind of delay?
Not for a regular school, but our NAVIC got canceled.
Oh, right. Yeah, because see, like for Holbrook, all of the reservation routes, and even actually Joseph City was like completely ice. Everything was ice. Both my wife and I left about maybe 10 minutes apart, and at the same spot, we almost each were independently in wrecks on the same intersection. Mine at the intersection, I mean, the accident I was almost in would have been my fault because I thought this guy was gonna pull out, but I think he was kind of scared, and so he's just like stays there. And so meanwhile, I just about plowed into him, and if I hadn't turned, I would have hit him. But then I had to back up because then there was a guy turning in, and I was in the wrong lane. My wife, on the other hand, she was there in the intersection, and a car lost control and she would have got T-boned. She would have got nailed. But then she just like drove out of the way. But the car totally lost control. So anyway, we felt lucky to get to school live today. But it was ice. It was pure ice. Okay, so what are we doing? Oh, practice 1F. So let's see. So Tobias, what do you have here?
I think it grows at the same rate.
Right, because when you break down using the change of base formula, then you can, if you invert and multiply, cancel the natural log of x's, you get the natural log of 3 over the natural log of 2. And that's a number. So if you get a number, then they have the same growth rate. Okay? All right. Any questions? So just to remind you about the change of base. So remember to always put the base on the bottom. So log base b of a is the natural log of a over the natural log of b. Log base 2 of 7 is natural log of 7 over the natural log of 2. So make sure you put the base on the bottom. Okay, functions growing at the same rate. If f grows at the same rate as g, and g grows at the same rate as h, then f and h grow at the same rate. Now, this might be kind of a duh type thing, but it's actually an important idea because sometimes functions, it's hard to compare them with each other. Okay? So like, for example, if I wanted to know which of these grew faster, those are hard to compare. I mean, if I try, see, look, I try and I plug in and I get infinity. Square root of infinity squared is infinity over infinity. So then I use L'Hopital. But then when I start taking the derivatives, it really isn't getting any easier. Okay? The x is going to go up here. This one's going to come down here. You could still work it out, but it's still going to be infinity over infinity. Only now, see, this one is going to be really tough to take the derivative of. So all I'm trying to say here is that this one's not easy to do. Okay? So instead, what you do is you compare them to a third function. Okay? And usually something easy like x. So we're going to compare both of them to just x, y equals x. Where's my oh, here we go. Okay, so if I take the radical and compare it to x, then see I get infinity over infinity. So I take the derivative. Okay. Oh no. Here, look at this right here. This is a good algebra trick. So let me just call your attention to this. That what we do is we rewrite x as the square root of x squared. That way we can put them underneath the same radical and then simplify and say, well, x squared over x squared is 1 plus 5 over x squared. And as x approaches infinity, this will approach 0. So 1 plus 0 is 1. So if we get a constant, they grow at the same rate. Okay? So now I do the same thing with the other one. All right, now, again, look at this step right here. So what I'm doing here is, since this is squared, a cool little algebra trick is to rewrite this as the square root of x squared. And since they're both squared, I can put them in the same set of parentheses. And then once again, I can simplify, split the fraction, and say this is just going to be 2 minus 1 over x. And then as x goes to infinity, I get 2 minus 0, which is 2. And then 2 squared is 4. Now you might say, well, wait, they were not the same. Well, remember, when you do the limit, if you get a constant, then we say that they grow at the same rate. So if the first two grew at the same rate and the second two grew at the same rate, then the two I'm trying to compare grow at the same rate. Okay? So that's the logic. So go ahead and try practice 2. And once again, you might want to try comparing those to x, like we did up here. Okay, so Weston, did you get it to work out?
Yep.
So you got a number for both of them?
Yeah, I did.
And they actually end up being 1 for both of them. But they don't have to be the same number. As long as they're both constants, then we consider that they grow at the same rate. Okay? All right. Either of you want me to go through that? Okay. Okay, so now really the last two parts is just a notation thing. Okay? So what's called little o and big O. All right, so little o, it says, as a function of a smaller order if this function grows slower, so the one that loses is a smaller order, and we say it's little o of the one that wins. Okay? So if we say f is little o of g, then that means g won. G grows faster, f goes slower. Okay? So let's say my question is, okay, I'm going to compare these and see which one is little o. All right, so we actually did this one similarly, where you get infinity over infinity, use L'Hopital's rule, take the derivative, and you get 1 over x or 0. Okay, so which one loses? ln of x or x?
ln of x.
So ln of x loses because we got a 0. So then you would say ln of x is little o of x. Okay? All right, so go ahead and do practice 3. Okay, so if it says show that x squared equals little o of x cubed plus 1, basically it's asking you to do what we've been doing, but when you do it, the x squared should lose. It should grow slower. Okay? All right, so basically when you get, if you put x squared on the top, you should get 0. If you put x squared on the bottom, you should get infinity. And then either way, you get x squared is little o of x cubed plus 1. All right? So, any questions from either of you? Okay, so that's little o. And then the last idea is big O. Now, big O is a slightly different because if they tie, then you can, so big O means that they're, the one that wins is big O of the other, or if they tie, if they're, then you could say one is big O of the other. So the way, I don't know if this helps you or not, but little o is just strictly less than. One function is less than, a smaller order, it grows slower. Big O is greater than or equal to. And the or equal to is where I would lose points on this when I was a student. Is that I never made that distinction just from the formula. Okay? But or equal to. All right? So if I'm comparing x plus sine x and x. So I plug in infinity, I get infinity over infinity. So use L'Hopital's rule. Oh, no, I didn't use L'Hopital's rule. I split the fraction. And so, because see, sine and cosine bounce around from 1 to -1. And so it's kind of hard to say what number is it approaching. Okay? So the reason why I split this one instead of using L'Hopital is that, see, this is 1 plus the maximum this could be would be, let's see, 1 over infinity, so 0. So that means this is going to be a number. It doesn't go to infinity. Okay? So then if I get a number, then that means they have the same growth rate. If they have the same growth rate, then you can say the top one is big O of the bottom one. Or you could even say that x is big O. You could actually reverse it. But x plus sine x is big O of x. It means that they have the same growth rate, or x plus sine x is faster. Okay? All right, so try that last practice problem. Okay, so Weston, did you get it to work out? Or are you still working on it?
Yeah, I think I got it.
Okay, so e to the x plus x squared over e to the x. So you can split the fraction here, and then you can see that this is going to be 1 plus something else. So it's not going to be 0. Can't be 0. And then when you're taking this limit, then you could use L'Hopital and say, well, this part, anytime you have a constant over infinity, this part is going to go to 0. And so, but you're going to get 1. You could have done it a different way, but you'd still get a constant. So if you get a constant, they grow at the same rate, and then you could say, so anytime one, if they tie, or if one grows faster, then you say that one is big O of the other one. Okay? So e to the x plus x squared is big O of e to the x. Okay? Any questions on that? So do some of those practice problems so you can kind of see different ways that we can ask those. But it's pretty straightforward. The other thing I want to just mention before we sign off here today is that so I guess that my work on that hiring committee for the VP is going to be really intense the week after spring break. So I was actually asked to get a substitute for that whole week. But what I think I'm going to do, at least for 2 of those days, is have our midterm be sometime during that week. So either Monday and Tuesday or Thursday and Friday. I mean, either Monday and Tuesday, probably Wednesday and Thursday would be my most likely scenario. So you probably have a sub on Monday and Tuesday, and then the midterm on Wednesday and Thursday. So we got a month to figure it all out and exactly what's going to be on that midterm. But if I schedule it then I won't have to miss classes, okay? Or more classes. So anyway, we'll talk about that later. So any questions before we call it? All right. Thanks, you guys. We'll see you tomorrow. Oh, hey, one other thing. I guess you can hear Weston. Is tomorrow morning I'll be sending out the guided notes for chapter 8. At least the first section or 2. So be kind of on the lookout for those.
Okay, I will.
All right.